All right, welcome back to our continuation of Chapter 3, Water and Life. Today we're going to be talking about Concept 3.3, Acid and Basic Conditions Affect Living Organisms. Something that you probably could have guessed, but do you really understand what that means, acid and basic? So, we know that water molecules can form hydrogen bonds with each other. Something interesting that can happen is when you have a hydrogen bond between a water molecule and another water molecule, that hydrogen atom in that bond can shift from one molecule to the other. Okay? When that hydrogen leaves, it leaves its electron behind and is transferred as just a single proton. Or, as another way of phrasing that, is a hydrogen ion, which has a full positive charge. Now, that hydrogen ion tends to stay with that water molecule, producing what is called a hydronium ion, which is H3O+. And so this would be considered an ionic compound, that we have a water molecule with an attached hydrogen ion. Now, even though this is what really happens, so we never have hydrogen ions just floating around on their own, we oftentimes represent it that way. So when we say H+, what we really mean is there is a hydrogen ion attached to a water producing a hydronium ion. All right. Now, when you take that hydrogen ion off, what's left of that original water molecule is the oxygen, another H, and an electron from that other hydrogen atom. That OH negative is called a hydroxide ion. So let's look at this graphically here. So we have a water molecule. Here's the oxygen. Remember, has a partial negative charge over here. Here's the second water molecule. The hydrogen has a partial positive charge. They form a hydrogen bond. Every once in a while, you will get a split, and that hydrogen ion, or that proton from the hydrogen, will remain with this other water molecule, producing a hydronium ion, which has a positive charge. And the other molecule left is the hydroxide ion, which still has the electron from this hydrogen, so it has a net negative charge. Okay. This happens back and forth. So when you have a bucket of pure water, it will happen, and then it will go back, and it may happen again, and it might go back. So this exists in what we call a dynamic equilibrium. It's constantly going back and forth. Okay. Now, in pure water, this actually does not go back and forth very often. So this happening in a bucket of pure water is fairly rare. Okay. However, when you introduce hydrogen ions, and remember this, when you produce a hydrogen ion, it would immediately attach to water to produce a hydronium ion. Or if we add hydroxyl from some other source, that can drastically affect this concentration. And when you get changes in concentrations of hydrogen and hydroxide ion, that can have a huge effect on a cell or living organism. Okay. So, when you have pure water, and you have this being formed, for every H+, we also have an OH-. So this is always equal. This means that the water itself is neutral in nature. It doesn't have any extra hydrogen ions, or it doesn't have any extra OH ions. Now, as I said before, certain substances, which we refer to as acid and bases, can release their own hydrogen ions or hydroxide ions and can alter this equilibrium. Okay? So the biologist and chemist and everyone else uses something called the pH scale to describe how acidic or how basic, which is the opposite of acidic, a solution is. So this kind of leads us to the question, well, what is an acid and what is a base? Okay? An acid is simply defined as any substance that can increase the hydrogen ion concentration. An example of this would be hydrochloric acid. As soon as you put this into water, it immediately breaks apart and forms a hydrogen ion and a chloride ion. Now, if you remember, this chloride ion would be surrounded by a hydration shell, and this hydrogen ion would attach to a water molecule and become a hydronium ion, so an H3O+. Alright, now, a base, which is kind of the opposite of an acid, is any substance that can reduce the hydrogen ion concentration. Okay? Example of this would be NaOH. Okay, this is also known as lye. So here, when you put this into water, it will break up into a sodium ion, and again, that sodium ion will form a hydration shell around it. Now, the OH ion will also form a hydration shell, and so you may ask, well, how does this affect hydrogen ion concentration? Well, the answer to that is when the hydroxide ion comes into contact with any excess hydrogen ions, it immediately reverts to water. So if you have any amount of hydrogen ions, the OH can pull it out of solution, which reduces the overall concentration of hydrogen ions, and that can shift something away from neutral. All right, strong acids and bases dissociate completely. So these two are both examples of that. So HCl, when you put in water, breaks apart completely. There's none left in this original conformation. Sodium hydroxide, the same thing. You put it into water, it immediately breaks apart, and there is none of the original left over. It's always existing in this. There are things called weak acids and weak bases that reversibly release and accept back the hydrogen ions. So in this case, you might have, let's say, 10 molecules of this weak acid, and maybe 5 out of the 10 have released their hydrogen ion, and the other 5 kept their hydrogen ion. Okay? What that means is hydrogen ions can reattach to what we refer to as a conjugate base of that acid that broke apart, so that acid can essentially, when it ionizes, it can reabsorb other hydrogen ions. And this can act as a way of moderating how the hydrogen ion concentration sits. So utilizing weak acids and bases, we can subtly affect the hydrogen ion concentration, and bases can do this by adding in OH. Now, we have this thing called the pH scale, and to understand the pH scale, we have to understand that in a pure water solution at 25 degrees Celsius, the concentration of hydrogen ions and hydroxide ions, if you multiply those concentrations together, and again, these would be molar concentrations, so mole per liter, and here, mole per liter of this. If you multiply that together, the result is always 10 to the negative 14th. Okay? Don't get too caught up on why that is right now. Again, chemistry can go into a little bit more detail on that. Why it's important to us is we have this thing called the pH scale. And working with numbers such as 10 to the negative 14th is fairly abstract. I mean, it would take you a while to even write that number down and count to make sure you had the proper number of zeros after the decimal point, right? So this is something abstract for our minds to wrap around. So we have this scale that adjusts the range to give us numbers that are easier for us to work with. So the pH is defined as the negative log of the concentration of hydrogen ions. So for a neutral aqueous solution, the hydrogen concentration or hydrogen ion concentration is 10 to the negative 7th. Why is that? Well, up here we just described that the combination of these two together is 10 to the negative 14th, so half of that is 10 to the negative 7th. Now, for those of you not familiar with log notation, if you take the log of 10 to the power of x, the result is it equals x. So a log calculation essentially removes this 10 base and just leaves us with the x. So let's go back to our equation here. pH equals negative log of the hydrogen ion concentration. And here we've already determined that is 10 to the negative 7th. So if we take the log of 10 to negative 7th, we are left with negative 7. We have a negative in front, so pH equals 7. So a pH of 7 is a neutral solution. All right. So an acidic solution is defined as anything that has a pH value of less than 7. A basic solution is defined as a pH greater than 7. Now, most biological fluids have a pH range of about 6 to 8. This seems to be the pH range that can support most life. Okay? So here's a neutral solution. We have equal numbers of hydrogen and hydroxide ions. Here is a basic solution. We have less hydrogen ions than we have hydroxide. Over here, we have more hydrogen ions, so that is an acidic solution. If you look at the scale, we can start putting some things into the scale to kind of give us an idea of what this might be. So here, pure water is about pH 7, slightly higher than that at a pH of about 7.4. We have things such as blood and tears. If we're looking at salt water or the inside of our intestines, it's a little bit more basic. Here, if we go all the way down to ammonia that you might get at the grocery store, that's even more basic. Bleach, even more so. And oven cleaner is a common household product that would be way down here. Oven cleaner is oftentimes a concentration of sodium hydroxide. All right, on the acidic end, our urine and our saliva is slightly acidic. Coffee is slightly acidic. Rainwater is, and we'll get to that here in a second. Tomato juice and beer, even more acidic. Vinegar, wine, cola is even more acidic. Lemon juice, even more. Interestingly, our stomach acid is around the same range as lemon juice. Finally, we get up to things like battery acid, and this gives us our pH scale. Now, buffers are things that can modify this pH or stabilize the pH, but we will pick that up in part 2.